Let R and S be different points on a circle omega such that RS is not a diameter. Let L be the tangent line to omega at point R, and point T is such that S is the midpoint of this line segment RT. Point J is chosen on the shorter arc RS of omega such that the circumcircle gamma of triangle JST, shown in blue here, intersects L at two different points, and A is a common point of gamma and L that is closer to R, which is shown here. Line AJ meets omega again at point K, and our goal is to show that the line KT, shown in red here, is tangent to omega, shown in blue. So how do we get started on this problem? Well, we can try using the tangency condition to get somewhere. So we want to show that directed angle KT something is equal to directed angle T something something. So what could this something here be? Well, if it were S, then we have a KTS works nice because S lies on RT, but angle TAS or TJS don't work out particularly well. So let's not try S. What about point J? Then angle KTJ doesn't work out nice because TJ is not really in our diagram. So let's go. So that leaves answer A. So we wish to show that KTA is equal to T something A. And since S lies on line RT, we'd like to show that this is equal to angle TSA because we can do a lot of nice things with line TS. So with that in mind, let's go ahead and draw line AT. Now that we have drawn in the segment AT, let's see what we can do with it. So we want to try showing that this angle here is equal to this angle here. And we don't know too much about KT right off the bat, so we might want to show that AT is parallel to something else in order to make this angle here a bit more manageable. And after a bit of searching, we might detect that AT is parallel to RK. So we conjecture that AT is parallel to RK. So how do we prove this? Well, this is actually a straightforward angle chase because we have directed angle TAK. We want to try using this because AJ and K are collinear and it can give us a lot of nice stuff. So then this is equal to directed angle TAJ because of the collinearity. And now we see cyclic quadrilateral AJST. So that is directed angle TSJ. And since RS and T are collinear, this is equal to directed angle RSJ, which is equal to, because of cyclic quadrilateral RJSK, directed angle RKJ. And this in turn is equal to directed angle RKA. And this implies that these two lines are parallel because TAK is equal to RKA. We have now shown that AT is parallel to RK, so we might want to try using something related to that. So at this point, we're stuck because we did not know what else to do here, because still the line KT seems very intolerable. At this point, we try looking at the information that we haven't used yet. And in this case, we haven't used the information that AR is tangent to omega, and more importantly, that S is the midpoint of line RT. And S being the midpoint of line RT seems rather strong for this problem, so we might want to try using it somehow. And since AT is parallel to RK, and we have a midpoint here, the thing that reminds us of midpoints and parallel lines is, well, parallelograms. So let's construct a parallelogram. So let's go ahead and let this point K prime here be such that RKTK prime is a parallelogram. Then we know that K prime T is parallel to RK, and AT is also parallel to RK from what we have shown. So A, K prime, and T are collinear. Furthermore, by properties of parallelograms, we know that K prime K bisects RT, and so K prime S and K are also collinear. now that we have this parallelogram in place, we can also construct the other side of the parallelogram. So this line here, such that RK prime is parallel to KT. So let's go ahead and list out these properties. So RK prime is parallel to KT, which gets rid of this red line here being randomly thrown in here. Then we also have that K prime S K are collinear. And so are K prime A and T. Let's see what we can do with it. Remember the main problem that we wanted to show, that directed angle KTA is equal to directed angle TSA. So let's see what we can do with both sides. So directed angle KTA, since KT is parallel to RK prime conveniently, this is equal to directed angle RK prime A. And directed angle TSA is equal to, since TS and R are collinear, this is equal to directed angle RSA. So this problem is equivalent to proving that these two are equal, and this is equal to proving that RAK prime S is cyclic, because we want these two to be equal. So how do we prove that RAK prime S is cyclic in the first place? Well, at this point, recall that we haven't used that AR as tangent to omega. So let's try to use this somehow. So directed angle ARS, which we want to show is equal to directed angle AKS. This is equal to directed angle RKS by the tangency, which is directed angle RKK prime. And because of the parallel lines, this is equal to directed angle AK prime K. And since K prime S and K are linear as shown here, this is equal to direct angle AK prime S. And we have shown that this quadrilateral here is cyclic, and we are done. So the highlights of our solution is as follows. First, we proved using basic angle chasing that AT is parallel to RK. Then we constructed parallelogram RKTK prime, inspired by S being the midpoint of RT. Using this parallelogram, we reduced the problem to showing that RAK prime S is cyclic, and we finally use the tangency condition here to prove this. And this solves the 2017 IMO Problem 4. So thank you so much for watching this video. Please subscribe if you'd like to see